and welcome to the 13th video of graph theory, where we'll discuss single source shortest path Bellman-Ford algorithm. So prior to this video, in video number 12, we have discussed single source shortest path Bellman-Ford algorithm question. That is, we have solved a question using Bellman-Ford. So what I am trying to tell you is that I always follow a reverse engineering method. In reverse engineering method, I first solve the question of any algorithm, using any algorithm, and then I'll discuss that algorithm. So because of this, to understand the algorithm become easy for you, no? So keeping that in mind, reverse engineering, let's start the algorithm, Bellman-Ford algorithm. So I request you, if you are directly coming to this video, kindly watch video number 12. So it will become easy, it almost 60% easy for you to understand Bellman-Ford. So let's start Bellman-Ford. So what Bellman-Ford says, first of all, you know that for every graph, even we have discussed same thing in Prim's algorithm, we have discussed same thing in Dijkstra, and now we are discussing same thing in Bellman-Ford, that you have given a graph, then you have given a weights of graph, and then you have given a source from where you have to start. First of all, what you do, initialize single source. What is initialize single source? You initialize every source with 0 and every other vertex with infinity. That is, for each vertex u belongs to graph, do what, key of every to the key of every, first what you do, initialize every node with every vertex with infinity, then every parent with nil, that is, you don't have any idea about parent of anything, and then source to 0. That is what I'm trying to tell you. Suppose you have given a graph. Now what do? You initialize source with 0. So what you are doing first, for every vertex, then what, initialize every vertex with infinity. So first of all, I'll initialize every vertex with infinity. Then what I am doing, I'm saying pi of u is nil, that I don't know about parent of any node. Because if somebody will ask me, currently if you will ask me who will be the parent of 1, I don't know. Who will be the parent of 5, I don't know. Definitely I don't know. And then key of s, that is source value, will be 0. This is what I was saying, that initialize source with 0 and all other node with infinity. So this is what single source is all about. So hope you understand the first step. And this is the third time when I'm discussing the first step, or you can say it's a fifth time when I'm discussing the third step. So if you have seen my previous video of Prims or Dijkstra, or those questions of Prims, or those question of Dijkstra, and even the question of Bellman-Ford, I've already discussed everything. Now for I is equal to 1 to Vg minus 1, what? Because in Bellman-Ford, what I've given you, what I've told you how Bellman-Ford is working. First, find out how many nodes you have. How many nodes you have in a given graph? 7 nodes. So what you have to do, you have to relax. You have to relax every edge. You have to relax every edge. How many number of time? 7 minus 1, 6 times. That is, you have to relax every edge 6 times. This is what we are taking. Loop is working from 1 to Vg minus 1, that is number of vertex minus 1. And then what you have to do, for each edge, that is, you have to see each edge which is in a graph, which is edge of graph, you have to relax it. And what is relaxed? I have already told you what is relaxed. Suppose there are two nodes, u, a and b, and their distance between them is, suppose 10, suppose this is 3, and suppose this is 16. So what is relaxed? You add both of them. 3 plus 10 is what? 13. Is this less than 16? Yes. So make it 13. Fine. If suppose this is 12, so add this 3 plus 10, 13. Is this 13 less than 12? No. So just keep it, just make it 12 only. Fine. So what this algorithm is all about, let's see this algorithm. So is dv, what is v? I'm talking of this b node. Is db, that is 16, greater than du? What is du? That is, what is a is 3, and what is wu? 10 is 3. Is this 16 greater than 13? Yes. Then what you have to do, you have to change the sum to this dv. So what will happen? This will become 13. Fine. Okay. And pi v, so the parent of b will become a, because a is the one who has determined b. Fine. So b will have a parent a. Fine. Okay. So this is what relax is all about. So hope you have analyzed what this algorithm is working. So let me show you a matrix which we have already developed. So what is the reason behind developing this matrix? Because you have to relax every edge. So what I did, I have make a matrix where each column of this matrix, where every column of a matrix contain all the edges, all that these are edges. So these are edges of a graph. So these are edges, so I have included all the edges, and how many number of time I have to relax these edges. Number of vertex minus 1. How many vertex are there? 7. So 7 minus 1 is 6. So I've made this 6 rows, for one row for every relax. Now you have a graph. You will use this graph to solve this relax, which I've already solved in Bellman Ford video number 12. So I've already solved this thing in video number 12. So I'm not going to relax this. I'm not going to iterate this algorithm, because I've already iterated it. I've already done everything. So if you're directly coming to this video, I'm again requesting you to kindly watch video number 12 of Bellman Ford algorithm, where we have solved a question. So this is the 13th video, and in 12th video we have already discussed a question on it. So this is my job is to explain you how this algorithm is working. So I've also explained you what is relax. I've also explained you initialize single source. Now it's your job to kindly watch the video and iterate this algorithm.